Hello, my name is Autumn Maruniak. I am a principal chemist at TDA Research, and I am the technical lead for this project, which is to develop a solid lubricant coating for wear and corrosion protection on gun parts used by the Navy. TDA is a small business outside of Denver, Colorado, established in 1987. We have a number of coatings, advanced materials, and chemical processes projects, many of them applicable to DoD research. We have 3 locations in the Denver area that consist of chemistry and engineering labs. And in these spaces, we do a lot of coating development as well as testing and characterization. The company has a lot of experience with licensing. We sell some of our products directly, and many of our products are qualified for military use. The challenge in this project is to develop a very thin, solid coating for various types of steel that provides corrosion protection and wear resistance to the part. Medium caliber guns, such as the N192-057, which is shown in the picture on the right, mounted on the Cobra helicopter, experience a lot of friction. They're currently lubricated with grease, but the problem with grease is that it ends up trapping a lot of sand, carbon, basically making little ball bearings that eventually erode the part. So the goal is to replace grease lubricant without altering the part or doing too much to change the nature of the gun. For that reason, the coating can only be 5 microns thick on certain parts of the breech bolt, body, and rotor track of the M197 rotary cannon. Other places can be a little thicker, but 5 microns is the maximum for certain parts on the breech bolt that experience the most wear. A few other restrictions that we've placed on ourselves is that the coating should be easy to apply. So for this reason, we are exploring solution processed applications such as dip or spray coating. Many thin solid lubricant coatings are applied through vapor deposition, which can require expensive equipment. Sometimes it's also difficult to coat things that are not line of sight, whereas with dip coating or spraying, you can get into nooks and crannies that can be difficult to access through these other methods. Solution processing is also, depending on the material that's used in the solution, can be a lot less expensive than some of these other coating methods. Additionally, some of the challenges that the Navy has given us is that the coating should prevent wear beyond the current maintenance interval, which is every 15,000 rounds. And after withstanding 15,000 rounds of wear, the coating should be able to withstand 7 days in a salt fog chamber, which is the standard test that's used to assess corrosion. It's basically a fog chamber that circulates warm, salty water around and can induce corrosion on unprotected metals. The reason that this coating is of interest is because the current coatings to protect these gun parts really don't offer that much protection. The steel used are different types of high-strength steel, 4140, 4340, and stainless steel. And they are pre-treated with conversion coatings, which are coatings that go on the surface of the metal and deposit a thin layer of a metal oxide that protects the surface from rusting. They get a top coat of grease, and they basically have to get serviced every several thousand rounds, and the parts wear down pretty quickly. So our goal, as I mentioned, is to hit 15,000 rounds as our initial goal. When at the time of this presentation we had hit 9,000 rounds, we have now passed 15,000 rounds and 168 hours of salt fog corrosion. Should also mention that the 15,000 rounds is performed at 200 degrees Fahrenheit, which is the maximum temperature that the gun gets up to when it's continuously running. And that's a much more difficult task than passing 15,000 rounds at ambient temperature, because the heat can play around with the coating and make it degrade faster. Our next goal is 30,000 rounds, which will require some optimization of the coating itself to give it more durability. Our coating system is shown very generically on the bottom. On top of the high-strength steel substrate, there is an anti-corrosion pre-treatment that is a zinc-nickel coating, and then we have a few microns of a solid lubricant coating that's based on an organic polymer with lubricious particles incorporated into the polymer. The pre-treatment is electroplated onto the steel. It's a very standard process using a brush electroplating method from Sifcoat ASC. And the solid lubricant top coat is just a dip coat that is cured at about 200 degrees Fahrenheit for an hour, and that's just to drive off some of the processing solvent. There's no actual chemical processes happening that are required to be heated. The prototype coating is shown on the bottom right. This is a standard panel that we coat. It's a flat steel panel with the coating over it. We etch an X into it. It gets down to basically the bare metal, and you put it in the salt fog chamber, and the hope is that the protective coating will keep that X from expanding, which would happen as the metal is degrading and there's rust. As I mentioned, the coating is a two-part system consisting of a 1 to 2 micron thick lower layer that is intended to protect against corrosion, and a 3+ micron thick top coat that's an organic polymer with anti-friction particles incorporated into the polymer composite. The process has changed a little bit now. The pre-treatment is a 5-minute brush plating instead of an immersion. We get better coating that way. It's a thin conformal coating. It's very commonly used. Zinc nickel is used now by a lot of DoD as a replacement for cadmium, and this is a low hydrogen embrittlement plating, so it doesn't cause any stress cracking in the steel. The coating itself is a polymer. It's abrasion resistant to sand and dust. It's a very high temperature polymer, so at elevated temperatures when the gun is running, it won't melt or soften. And it's also hydrophobic, so in addition to the corrosion protection afforded from the lower sacrificial metal layer, the zinc nickel, the polymer composite on top is hydrophobic, and so it repels water. On the right is a picture of one of the parts that we coat. This is a rail, so it's part of the gun that is responsible for pushing the bullet into the chamber. It's part of that assembly. These are parts that we machined on a custom wear tester that basically can heat up the parts and run them at the same rate that the gun would be firing. So the bare part is shown on the top, and then the pre-treatment with the zinc nickel is shown on the bottom. This is a picture of the wear simulator that we built at TDA. You can see the simulator in action if you go to the YouTube link on the bottom of this slide. It's built to replicate a breech bolt and rotor track or slide rail sliding wear. We machined pieces based off of the exact dimensions of the breech bolt body and rotor track used in the N197 gun. We coat them and we hook it up to this simulator, and you can set the temperature, you can set the number of cycles that you want it to run. So there are 3 chambers to this gun, so 15,000 rounds divided by 3 would be 5,000 cycles, and that's where we get those numbers from. This is one of the earlier tests that we ran with our coding system. It's actually changed quite a lot since these pictures were taken. So this is a picture of the rotor track after 9,000 rounds of wear, or basically 3,000 cycles on the wear tester, and then after 24 hours in the salt fog. So you can see where the wear shows kind of on the edges there and where you're getting down to bare metal. So now with a slightly changed coding, we can get to 15,000 rounds. You really don't see that much wear, and we can pass 7 days in the salt fog chamber, which is the ASTM B117 method. We estimate that we're currently at TRL 4. We've demonstrated the coding on a simulated breech bolt body and rotor track in the lab environment. We can get protection up to 15,000 rounds. We're working on 30,000, that's the next goal. We've also demonstrated the coding properties like adhesion and corrosion protection and some of the other tribological properties that are of interest on flat coupons and the simulated parts. At the end of the project in August, we expect to be to TRL 5. At the end of phase 2, we will be coding an actual gun with our prototype coding, and we will be doing a dry cycle endurance test of 15,000 rounds plus a salt fog post-fire test. After our phase 2 option, we expect to be at TRL 6. During the phase 2 option, we plan to further optimize the coding based on lessons learned during the dry cycle endurance test, and then coat another gun and do another endurance test with an optimized coding. This chart is a summary of the key features, advantages, and benefits of our coding system. The key feature is that it's a permanent or semi-permanent coating. It can be removed to replace grease. There are a lot of applications that this coating could be applied to that would benefit, especially in extreme environments where there are moving parts in either marine environments or in deserts. The coating doesn't trap sand like grease does, so it extends the lifetime of the part, and as a result, this lowers maintenance frequency and cost. The system contains anti-corrosion chemicals, so this adds an extra layer of corrosion protection for the metal parts, which again lowers maintenance frequency and costs. The coating itself contains anti-wear nanoparticles such as graphene and molysulfide. This enables the parts to glide smoothly over each other and reduces the amount of wear, which lowers maintenance frequency and costs. The coating system is easy to apply. It can be applied through dip coat, brush plating, or spraying, depending on which part of the coating it is and what the user prefers to do. Because it's a solution-based process, it's fast and easy to apply, and it doesn't require expensive or unusual equipment, especially equipment the Navy depots would not be familiar with. This means it's a less expensive process, it's also less labor intensive, and it can be performed by a minimally trained technician. Eventually, the coating will last for 30,000 rounds, so this will extend the lifetime of the gun beyond what it currently has, which again will lower maintenance frequency and cost. The plan to transition this technology to the fleet is to do several runs initially of optimization, applying the coating to the N197 gun and running a series of endurance tests. If funded in the phase 2 option, we will do additional optimization of the coating based on the phase 2 test results and continue to test this coating on an assembled gun for an endurance demonstration. Traditionally, TDA commercializes our products through a licensing model, although we do also do direct sales depending on the volume and the customer. What's really exciting about this technology is that there are a number of commercial applications for the coating system. Other guns, for example, there are other guns that share the same structure as the 197. Small, medium, and large caliber guns would all benefit from this technology. There's also a lot of different types of equipment in machining, mining, underwater, which requires greaseless, and automotive applications that would all benefit from this technology. The nice thing is that a lot of these other applications are not limited to the really thin tolerance that the M197 gun has, so you would get even better performance if you could even just double the thickness of the coating from 5 to 10 or 10 to 20 microns. This application method is also ideal for complicated parts and geometries. Like I said, a lot of the solid lubricant coatings for machining and other high-tech processing equipment and industrial equipment currently uses diamond-like coating, which has to be applied through plasma vapor deposition. So if you have some unusually shaped parts with non-line of sight areas, this application method is ideal for those because you can do a dip coat. You can also do a hand spray. Though this project is still in its early stages, we are seeking a prime contractor to apply the coating to gun parts during manufacture. Our initial target is a prime contractor for the M197 rotary cannon. Other targets could include any contractor that manufactures medium caliber guns that might be used in dusty or dirty or marine environments. The contractor would provide parts for coating and would assist with validation testing, and we would provide the coating formulation and the method for application. We're very interested in working with other folks on this project, finding out what other applications people think that this could be useful for, or if anyone is excited to try this and have us coat some prototype pieces, we'd be very happy to do so. You could reach out to me. Again, my name is Autumn. I'm now a principal chemist at TDA. I've listed my mobile and my email address. Those are the best ways to reach me. You could also email Dr. Girish Srinivas, who's the CEO of TDA. We're located, again, as I mentioned, in Wheat Ridge. We also have a couple of locations in Golden, and you can always find us online at tda.com. Thanks very much.